Welcome to our CVPR 2024 presentation. We're thrilled to share our work aligning Logits generatively for principled black box knowledge distillation. We'll start with the concept of black box knowledge distillation. It's about distilling knowledge from a black box teacher on a cloud server into a lightweight student model on an edge device. The student doesn't have access to the teacher's structure or parameters. The model compression process is accomplished by sending queries to the cloud servers. Practical B2 KD applications come with constraints. Limited data exchange over the internet due to latency and bandwidth restrictions is a common issue. API services, typically provided by service providers, come at a cost. Most APIs offer semantic tags instead of probability vectors. The disparity in data distribution between edge and cloud data presents a significant challenge to knowledge distillation. Data privacy concerns further complicate the estimation process. Existing methods to overcome these challenges fall into three categories. Response-based KD derives the student to mimic responses of the teacher. Black box KD hides the teacher in cloud servers and sends queries for distillation. Adversarial KD exploits adversarial architecture for knowledge transfer from whitebox teacher. Adversarial KD, also known as GON-based KD, integrates the teacher-student architecture into generative adversarial training, utilizing the discriminatos gradients to align the output distributions of the student and teacher. In our formal analysis of the B2 KD problem, we established two definitions to quantify the mapping relationships. Definition 1 posits that given identical input distributions, the proximity of the Wasserstein distance between the output distributions of the teacher and student models is indicative of the closeness of their respective mapping functions. Definition 2 suggests that when a generator utilizes the teacher's output distribution as input, the closer the generated distribution aligns with the real distribution, the more accurately the generator's mapping approximates the inverse function of the teacher's mapping. Building on our definitions, we delve into the conditions for empirical equivalence between teacher and student mappings. When a generator uses the logits of both the teacher and student as input, and the distance between the two resulting finite sets approaches zero, we can consider the mappings of the teacher and student to be consistent. A well-trained generator maps a cell decomposition in the latent space to a corresponding decomposition in the image space, with each cell mapped to a sample via the decoding map. This leads us to propose a new optimization direction, moving from logits to cell boundaries. This approach aims to align low-dimensional logits by minimizing the distance between two generated images in high-dimensional space. Furthermore, we posit that an image, rich in fine-grained information, can serve as an additional knowledge source, providing diverse gradient directions for updating the student model parameters. The combination of image-level loss with coarse-grained logit-level loss can significantly enhance the distillation effect. Simultaneously, we offer a generalization bound for this method. With a probability of at least 1 minus delta, the generalization error is valid for all hypotheses. Our approach is a two-step process. The first step, deprivatization, involves adversarial training of a generative adversarial network and the application of information maximization loss to enhance the quality of synthesized images. The IM loss leverages the teacher model's response to gauge the quality of the generated images, with lower response samples incurring higher losses. The second step employs a well-trained generator and utilizes the optimization direction outlined in Theorem 2 to aid black box knowledge distillation. We assess the equivalence of the student and teacher functions by calculating the distance between the output points of the student and teacher's logits via the generator, optimizing this as a loss. In our research, we conducted extensive experiments across various teacher-student pairs and multiple benchmarks. Despite the limited number of images available, our MEKD outperforms previous B2 KD methods, effectively reducing the number of samples required to be stored on edge devices. We also explored the advantages of our method over other KD methods, particularly in scenarios with limited query samples and out-of-domain distillation. Even with a limited sample size on edge devices, MEKD demonstrated superior performance. We also examined the impact of different hyperparameters and conducted comparative ablation studies. In conclusion, We have theoretically formalized the B2KD problem and proposed the MEKD method. By treating a generator as the inverse mapping of the teacher function, we avoid leaking information about the teacher model structure or parameters. The importance of a well-trained generator cannot be overstated. Even with a smaller student model, MEKD enhances distillation compared to other B2KD methods. Thank you for watching.